Hello friends, welcome to our incredible journey through the realms of wormholes and time travel. In this video, we will explore the fascinating concepts that bridge the gap between science fiction and reality, shedding light on how wormholes could potentially be used as shortcuts through space and time. We'll delve into the theories proposed by brilliant minds like Einstein, Hawking, and Kip Thorne, and uncover the mysteries of these enigmatic passages. Join us as we venture into the science of space-time, the potential for time travel, and the mind-bending possibilities that lie within the heart of the universe. Let's embark on this thrilling adventure together and unlock the secrets of wormholes and time travel. Imagine a universe where you can travel from one point in space to another in the blink of an eye, or even journey to the past and witness historical events firsthand. This is the tantalizing promise of wormholes and time travel, concepts that have fascinated scientists, writers, and dreamers for decades. Let's begin our exploration by understanding the fundamentals of wormholes. Wormholes are theoretical passages through space-time that could create shortcuts for long journeys across the universe. They are often depicted in science fiction as tunnel-like structures with two ends, each located at different points in space-time. The idea of wormholes comes from solutions to the equations of Albert Einstein's general theory of relativity, which describes how gravity affects the fabric of space-time. The concept of a wormhole was first proposed by physicists Albert Einstein and Nathan Rosen in 1935, hence the term Einstein-Rosen bridge. According to their theory, wormholes could connect two distant points in space-time, potentially allowing for faster-than-light travel. This idea was groundbreaking because it suggested that space and time are not fixed and immutable, but can be warped and connected in unimaginable ways. To understand wormholes, we need to delve into the nature of space-time itself. Space-time is a four-dimensional continuum that combines the three spatial dimensions, length, width, and height, with the dimension of time. According to Einstein's theory, massive objects like stars and planets can warp the fabric of space-time, creating what we perceive as gravity. This warping effect is similar to placing a heavy object on a stretched rubber sheet, causing it to dip and curve around the object. In the case of a wormhole, imagine folding that rubber sheet in such a way that two distant points touch each other. A tunnel through this fold would be a wormhole, providing a shortcut between the 2 points. While this analogy helps visualize the concept, the reality of creating and maintaining a wormhole is far more complex and currently beyond our technological capabilities. One of the most intriguing aspects of wormholes is their potential for time travel. If a wormhole could connect different points in time as well as space, it might be possible to travel to the past or future. This idea has been explored extensively in science fiction, from H.G. Wells' The Time Machine to the Back to the Future movies. However, time travel through wormholes also raises numerous paradoxes and challenges that scientists are still trying to understand. For a wormhole to allow time travel, it would need to be traversable, meaning it could be safely crossed by matter and information. This requires a stable structure and the presence of exotic matter, a hypothetical form of matter with negative energy density. Exotic matter is crucial because it could counteract the gravitational forces that would otherwise cause the wormhole to collapse. Exotic matter is not the same as antimatter, which is composed of antiparticles with opposite charges to normal particles. Instead, exotic matter would have properties that violate known laws of physics, such as producing negative pressure. While exotic matter has not been observed directly, some phenomena in quantum mechanics suggest that it could exist. One of the key challenges in creating a traversable wormhole is finding a way to stabilize it. Wormholes are predicted to be extremely unstable, prone to collapse as soon as they form. This instability is due to the immense gravitational forces at the wormhole's throat, the narrowest part of the tunnel. To keep a wormhole open, we would need an enormous amount of exotic matter to counteract these forces, a requirement that currently seems impossible to meet. Despite these challenges, the idea of wormholes remains a captivating area of research. Physicists like Kip Thorne have proposed various theoretical models to explore the possibilities of wormholes and time travel. Thorne's work gained widespread attention through the film Interstellar, where he served as a scientific consultant to ensure the depiction of wormholes and black holes was as accurate as possible. Black holes, another fascinating prediction of Einstein's theory, are closely related to wormholes. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape its pull. The boundary of a black hole is called the event horizon, beyond which lies the singularity, a point of infinite density where the laws of physics break down. Some theories suggest that wormholes could form at the event horizon of a black hole, connecting it to another point in space-time or even to another universe. This idea, known as a white hole, represents the other end of a wormhole. While black holes consume matter and energy, white holes theoretically expel them, creating a continuous flow through the wormhole. The connection between black holes and wormholes is speculative but intriguing. It raises the possibility that black holes could serve as gateways to other parts of the universe, or even to parallel universes. The concept of parallel universes, or the multiverse, suggests that our universe is just one of many, each with its own unique properties and laws of physics. The idea of the multiverse is supported by some interpretations of quantum mechanics, particularly the many worlds interpretation. According to this interpretation, every possible outcome of a quantum event actually occurs in a separate parallel universe. If wormholes could connect these parallel universes, they would provide a means of traveling not just through space and time, but across different realities. Quantum mechanics plays a crucial role in our understanding of wormholes and time travel. One of the key principles of quantum mechanics is entanglement, a phenomenon where particles become interconnected in such a way that the state of one particle instantly affects the state of another, regardless of the distance between them. This spooky action at a distance, as Einstein called it, suggests that information can travel faster than light, a concept that could be related to wormhole travel. In recent years, scientists have begun exploring the possibility that wormholes could be used for quantum communication, allowing information to be transmitted instantaneously across vast distances. This idea is still in its infancy, but it represents a promising avenue for future research. Another fascinating aspect of wormholes is their potential connection to cosmic strings, hypothetical, one-dimensional defects in the fabric of space-time. Cosmic strings are predicted by some theories of the early universe and could have formed during phase transitions shortly after the Big Bang. These strings would be incredibly thin but immensely dense, with a gravitational pull strong enough to warp space-time. If cosmic strings exist, they could play a role in the formation and stabilization of wormholes. By threading a wormhole with a cosmic string, it might be possible to keep the wormhole open without the need for exotic matter. This idea is highly speculative, but it represents another potential pathway for future research. The concept of wormholes also intersects with the study of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects. The detection of gravitational waves by observatories like LIGO has opened up new possibilities for understanding the nature of space-time and the existence of wormholes. If a wormhole were to form or collapse, it could produce distinctive gravitational wave signatures that might be detectable with advanced technology. As we continue to explore these fascinating concepts, It's important to remember that our understanding of wormholes and time travel is still in its infancy. While the theories are based on sound scientific principles, we have yet to find concrete evidence that wormholes exist, or that time travel is possible. The challenges of creating and stabilizing wormholes are immense, and the requirements for exotic matter and advanced technology are currently beyond our reach. However, the pursuit of these ideas is valuable in itself. It pushes the boundaries of our knowledge and inspires us to think creatively about the nature of the universe. By exploring the possibilities of wormholes and time travel, we are not just seeking answers to fundamental questions about space and time, but also expanding our imagination and our vision of what is possible. The development of theories about space-time has a rich history, beginning with Newtonian physics and culminating in Einstein's general relativity. Newtonian physics viewed space and time as separate, absolute entities, unchanging and unaffected by objects within them. In contrast, Einstein revolutionized our understanding with his theory of general relativity, which proposed that space and time are intertwined in a four-dimensional continuum known as space-time. He demonstrated that massive objects could curve this space-time fabric, giving rise to what we perceive as gravity. Science fiction has played a pivotal role in popularizing the concepts of wormholes and time travel. Works like Interstellar, The Time Machine, and Back to the Future have captivated audiences while introducing them to complex scientific ideas. These portrayals, while often speculative and fictional, help spark public interest and inspire scientific research. The influence of science fiction on public interest and scientific research cannot be overstated. By imagining future possibilities and exploring theoretical concepts in a narrative form, science fiction often inspires real-world scientific exploration and innovation. Einstein's field equations play a crucial role in predicting wormholes. These equations describe how matter and energy influence the curvature of space-time. Solutions to these equations, such as the Schwarzschild solution, describe the space-time around spherical, non-rotating masses, leading to the prediction of black holes and wormholes. The mathematical framework of general relativity includes the concept of the metric tensor and the geodesic equation. The metric tensor provides a way to measure distances in curved space-time, while the geodesic equation describes the paths that objects follow under the influence of gravity alone. The concept of quantum foam has significant implications for the structure of space-time at the Planck scale. Quantum foam, also known as space-time foam, refers to the idea that at extremely small scales, space-time is not smooth but frothy and turbulent, with transient wormholes popping in and out of existence. This concept suggests that space-time itself is a dynamic, ever-changing entity, constantly influenced by quantum fluctuations. Quantum field theory plays a crucial role in understanding the properties of exotic matter. Quantum field theory combines quantum mechanics and special relativity to describe how particles and fields interact. It provides a framework for understanding the behavior of exotic matter, which is hypothesized to have negative energy density and could stabilize wormholes. The potential technological advancements required to detect or create wormholes are immense. This includes advancements in particle accelerators, which could help us understand the properties of exotic matter, and advancements in gravitational wave detectors, which could detect the signatures of wormholes forming or collapsing. Advanced materials and energy sources are crucial for theoretical wormhole construction. Materials with extremely high tensile strength and resistance to radiation could be essential in building a structure to stabilize a wormhole, while harnessing massive amounts of energy, perhaps from fusion or antimatter reactions, could be necessary to create and maintain a wormhole. The potential societal impacts of time travel include significant ethical dilemmas. such as the temptation to alter historical events or the consequences of interacting with past or future versions of oneself. Altering past events could have unforeseen and potentially disastrous consequences, creating paradoxes and altering the course of history in ways that might be impossible to predict or control. The ethical considerations of altering the past or future are profound. If time travel became possible, it could lead to significant changes in history and personal identity, raising questions about the nature of reality and our place in it. The historical milestones in the understanding of black holes are equally fascinating, from John Michel's dark stars to modern observations. Michel, in the 18th century, was among the first to propose the idea of dark stars, celestial bodies so massive that not even light could escape their gravitational pull. This idea was further developed in the 20th century with the theoretical work of Carl Schwarzschild and the observational discoveries of Cygnus X1 and the supermassive black hole at the center of our galaxy. Ongoing research in theoretical physics related to wormholes and time travel includes work on quantum gravity, string theory, and loop quantum gravity, which seek to unify general relativity with quantum mechanics. These areas of research are at the forefront of our quest to understand the fundamental nature of the universe. Upcoming experiments and observations might provide evidence for or against the existence of wormholes. Advancements in telescopes and gravitational wave detectors could reveal new insights into the nature of spacetime and the potential for wormholes and time travel. Wormholes and time travel remain some of the most captivating and challenging concepts in modern physics. They represent the intersection of science fiction and reality, offering tantalizing glimpses of what the future might hold. While we have much to learn and many obstacles to overcome, the journey of discovery is one that promises to be as exciting and rewarding as the destination itself. So stay curious, keep exploring, and let your imagination soar as we continue to unlock the secrets of the universe. Thank you for joining us on this journey through wormholes and time travel. Please like, comment, and share the video, and please do not forget to subscribe for more videos.